so we talked about what wavefronts are, right? And we've only talked about plane wavefronts. So here is plane waves. And so for plane waves, the wavefronts are these parallel planes. If you have a point source of light, then what it gives out are spherical waves. So that's analogous to you disturbing the surface of a of a lake and creating these circular waves. So in 3 dimensions, the analog of circular waves is spherical wavefronts. And so if you have a point source of light, that's going to produce these spherical wavefronts. So the wavefronts will not be planes, but they will be spheres. But on the other hand, if you're quite far away from the source, then at your location, they will look like planes, right? So at your location, you won't be able to tell that these are actually parts of spheres. So if you're sufficiently far away from a source, then the wavefronts appear to be plane waves. That's why plane waves are very convenient to study. Okay, so when you have plane waves, it's actually hard to just imagine these large infinite planes moving towards you. So it's much more convenient to just think in terms of rays, which are lines drawn perpendicular to the wavefronts. So if you have these plane waves, which are indicated by these green lines over here, and they're all moving to the right, it's much easier to think in terms of these rays, which are just normals drawn to these plane waves. So that's what we're going to do from now. So instead of drawing the plane waves, we are going to draw normals to those waves. All right. So the first property of light that we're going to study is called reflection. And reflection is the absorption and re-emission of light by the atoms in a reflecting medium. So you're all familiar with reflection. So suppose you have a source of light over here, like a laser pointer or a flashlight. If you shine it towards a surface, it will sort of bounce off the surface and go in this direction, right? So this bouncing off is called reflection. Why does light reflect? That is a bit complicated. So what happens is that when light hits a certain surface, like a table or your body or anything, the electric fields in the light will make the electrons in that surface vibrate, right? And the vibration of those electrons is going to produce new light, right? And that is the reflected light. That makes sense? So that is how light reflects. So when light hits the surface of my hand over here, it's making the electrons on the atoms and molecules near the surface of my hand vibrate. And those vibrating electrons, you know that vibrating charges produce electromagnetic waves. And so those vibrating electrons in my hand produce more light, and that is the reflected light. That makes sense? So reflection is the absorption and re-emission of light by the atoms in the reflecting medium. Now, the basic rule of reflection is the angle of incidence equals the angle of reflection. So this is the, generally you always draw normal to the surface. So this is the normal to the surface. And all these angles of reflection and refraction and incidence are always measured with respect to the normal. So this angle right here is called the angle of incidence. It's the angle made by the incident ray of light to the normal. And this angle right here is the angle of reflection. And it's the angle made by the reflected ray to the normal. Notice that angles are always measured with respect to the normal to the surface. And the law of reflection states that theta I is equal to theta R. That makes sense? All right, and you can ignore this. Is everybody clear about that? Theta I is equal to theta R. That's called the law of reflection. All right. Okay, we'll just talk about another property, and that's refraction. So when light goes from one medium to another, it undergoes a change of speed. That is because the speed of light is different in different mediums, right? In vacuum, the speed of light is 3 times 10 to the power of 8 meters per second. But as it travels in different transparent media like glass or water, its speed is a little bit lower, right? Not that much lower, but somewhat lower. So this change in speed causes a change in direction. So in general, when light goes from one medium to another, its speed and direction both change. And so that phenomenon is called refraction. So refraction refers to the change of speed as light goes from one medium to another, and potentially a change of direction, right? So here is an incident ray that's coming in, and the angle of incidence is this angle theta. Notice that angles are always measured with respect to the normal. So θ1 is the angle of incidence. And as it goes into medium 2, you can see that it has changed direction. So it's bent closer to the normal right now. And the angle of refraction is θ2 right here. That makes sense? So this phenomenon where the speed and the direction changed is called refraction. Now, the change of direction is related to the change of speed. So sine θ1 divided by sine θ2 is equal to v1 over v2, where v1 and v2 are the speeds of light in the two media. So sine θ1 divided by sine θ2 is v1 over v2, and this is called Snell's law. Okay, now why does the light change direction? You can easily see that if you look at this. If you look at this somewhat psychedelic animation. So what's happening is that the wavefront is moving with a certain speed, and then when it goes into the other medium, the part of the wavefront in the new medium is moving with a slower speed, whereas the rest of the wavefront is moving faster, and so the whole wavefront turns. So one very simple example of that is like, suppose you're pushing this shopping cart there, and there are wheels over here, and suddenly you hit, so you were pushing it on the concrete, but suddenly these wheels under the dashed line hit the grass, right? So now these are moving slower, and these wheels are moving faster because they're still on the concrete. And so what's going to happen to the shopping cart? It's going to turn in this direction. That makes sense? And so when one part of the wavefront is in the slower medium and the rest of the wavefront is in the faster medium, the whole wavefront turns. And that is why you have refraction. All right, one last thing, and I promise it won't take more than a minute. Notice from this equation that if θ1 is 0, that means if the light is coming in like this, that's called normal incidence, then θ2 will also be 0, right? If θ1 is 0, then θ2 will also be 0, because sine θ1 times v1 is equal to sine θ2 times v2. So if θ1 is 0, you know that v1 and v2 are not 0, so sine θ2 must also be 0. So in that case, the light will just go straight through. That is the one case where you won't have a change of direction. But other than normal incidence, you will always have a change of direction.
So you have a ray of light coming in. The angle that it makes with the normal to the interface between the two media is, let's say it's θ1. And then when it goes into the water, it's going to change direction. And it might be going in this direction. And this change in direction happens because of a change in speed. So as light, as a wave goes from one medium to another, its speed changes. And the speed of light in air is a little bit faster than in water. So let's say that this angle is θ2. And this is the angle made by the refracted ray, the ray that went into the water with the normal. So that's θ2, right? Now, whenever the light hits the interface, some of the light will also be reflected. So that I didn't draw that over here, but for completeness, I should also draw the reflected ray here, which will make the same angle as the incident ray. And that is the law of reflection that we also discussed yesterday. But we are not going to bother with the reflected ray for now. We'll just focus on the one that went inside. But there'll always be a little bit of reflection whenever you have refraction. All right. So Snell's law says that sine θ1 divided by sine θ2 is equal to v1 divided by v2, right? So Snell's law, but it's written in a slightly different way. So I'll just introduce that for now. So this is Snell's law. Now, I told you that the speed of an electromagnetic wave is different depending on the medium that it's traveling in, right? The index is the ratio of the speed of light in vacuum to the speed of light in the medium. That's the definition of index of refraction. So the index of refraction n, that's the symbol for the index of refraction, is defined as the speed of light in vacuum, which has its own letter c, divided by the speed of light in a particular medium. So you can clearly see that n will always be greater than 1, right? Because it's not possible for it to have a speed greater than c. So n will always be greater than 1. So n is called the index of refraction. And n does not just depend on the material, also depends on the wavelength or the frequency of the light that's being used, that's propagating through that medium, right? So now the frequencies or wavelengths of visible light, and we are only going to be talking about visible light for the most part, they're all very close to each other, because we saw that the wavelength range for visible light is something like around 400 to 750 nanometers, something like that. So the wavelength range, wavelengths of all the visible light waves is pretty much the same, very close to each other. And so their frequencies are also very close to each other. And so the refractive index only slightly differs for different wavelengths of visible light. That makes sense to all of you? So it's slightly different for blue light. For a given medium, it's slightly different for blue light than what it is for red light. All right, so the refractive index depends on the material, and it also depends on the wavelength of light that's propagating through the material, right? All right, and a convention is that sometimes when you have a larger n, so one medium has a larger value of n than the other medium, you sometimes just call it optically denser. So that's just a convention. So that's easier than saying larger value of n. So for example, water is optically denser than air because water has a n of 1.33 and air has a n which is very close to 1. So we would say water is optically denser than air. That clear to all of you? So the index of refraction for a certain medium is the speed of light divided by vacuum divided by the speed of light in vacuum divided by the speed of light in the medium. That's the definition of n, and it depends on the medium. It also depends on the frequency of light or wavelength of light. That clear to all of you? Okay, so it's more convenient to express Snell's law in terms of n. So we've just seen that V is equal to C divided by n, right? So if this medium has n of n1 and this has n of n2, right? N value of n2, then you can see that V1 divided by V2 is equal to, I'll just write it over here, V1 divided by V2 will be n2 divided by n1, because V and n are inversely proportional to each other, right? So instead of using V's, it's conventionally, Snell's law is expressed in terms of n's. And so Snell's law is written as n1 sine theta 1 is equal to n2 sine theta 2. So this is the way Snell's law is usually written, right? But this is also Snell's law. So they are both Snell's law. Is that clear to all of you? All right. So Snell's law is the law of refraction. Okay, so we just talked about this. All right. I'll let you do this plug and chug problem yourself. It's also worked out on the slide. All right, let's try this question. The question is asking whether it's bending away from the normal or towards the normal. All that means is the angle theta 2 greater than the original angle of 30 degrees? Or is it less than the original angle of 30 degrees? Because if it's greater, then it's going to bend away from the normal. And if it's less, then it's going to bend towards the normal. So we just need to figure out what is the relationship between theta 1 and theta 2, right? Is theta 2 greater than theta 1, or is it less than theta 1, right? Greater than theta 1 would mean away from the normal. Less than theta 1 would mean towards the normal. So to answer that, we just apply Snell's law. So n water sine theta 1 is equal to n air sine theta 2. And so you can see that sine theta 2 is equal to n water divided by n air sine theta 1. And you know that n water is larger than n air, right? And so n water over n air will be greater than 1. And so you can see that sine theta 2 will be greater than sine theta 1. That makes sense? And so if sine theta 2 is greater than sine theta 1, you know right away that theta 2 is greater than theta 1, because you know that in the first quadrant, sine theta and theta behave more or less the same way. If theta goes up, sine theta goes up. So if sine theta 2 is greater than sine theta 1, then theta 2 is greater than theta 1.